Okay, let's start. Today we are going to do the line integrals again with explicit computation. So first look at the following example. So evaluate the integration along C of y squared dx plus x dy. So from the expression, it's of second kind. Okay, where? So we have two small questions. So first, C1 is a line segment from -5, -3 to 0, 2. And B, C2 is the arc of the parabola x equals 4 minus y squared from -5, -3 to 0, 2. Okay, let's draw the picture. So -5, -3, suppose it's here. 0, 2 is here. Okay, so first problem A is a line segment connecting them directly, and then so this is C1. C2. So you noted that they had the same starting point, same end point. And if you draw, it's a parabola that moves towards the negative x direction. And the y-intercept is 2 and -2. So my bad drawing, sorry. Excuse my bad drawing. So here is 4, 0, 0, -2. Okay, and then we carry out the calculation. So for problem A, we first parameterize the curve C1. So how to parameterize it? It's easy to see. You can take the following. You can take the formula we used before. So recall. So gamma t. If the curve is a line, then you can use you can interpolation the endpoint and the initial point as follows. So 1 minus t times the initial point plus t times 0 to 2. And if you let t, the parameter is from 0 to 1, then this parameterization also includes the direction from the initial point to the ending point. Okay, if you do t times -5, -3 plus 1 minus t 0 to 2, then we have the same line but with different direction, goes this way. We will discuss in detail the orientation stuff, but now we just take this parameterization. Okay, then if you write down in coordinates, what do you have? You have x is 5t minus 5, y is 5t minus 3. Of course, you have the interval t is from 0 to 1. And now our line integral can be written down as follows. The integration is from 0 to 2 with respect to dt. And then inside, you have y 5t minus 3 squared times dx dt plus x is 5t minus 5 times dy dt, and then whole thing dt. Note that inside we must transform it function of t. Okay, then what do you have? We need to compute a little bit dx dt, but here the computation is straightforward. You have 5 plus 5t minus 5 times 5 dt. Okay, here you can use the power rule and chain rule directly. So 5t minus 3 cubed divided by 3. This corresponds to this term. And then the next one, 5t minus 2 squared over 2, correspond to this. This is antiderivative, and you plug in 1 and 0. Sorry. Okay, when you plug in 1, you have 2 cubed over 3, and when you plug in 0, you have negative 3 cubed over 3 plus negative 5 over 3 over 2. So 8 over 3 plus 27 over 3 plus 125. Oh, sorry, here's 2 squared. over 2. It's minus. So finally, the final answer is negative 5 over 6. Okay, now let's do problem B. And here for B, recall our curve looks like this. Negative 5, negative 3, this is initial, and the ending is here, 0, 2. Therefore, you see the direction is this one. And then the parametrization, since x is 4 minus y squared, then probably you can choose parametrization as you choose y variable as a parameter, and then x is a function of y. And then for y, you see the direction is from initial point to end point. Then naturally you have negative 3 between negative 3 and 2. And then similarly, we can carry out the computation. So it will be from negative 3 to 2, y squared dot x dx dt. So we can compute a little bit. Dx dt is negative 2y. Dy dt is 1. So 2y plus x times 1. It's too long. Dt. And then let's plug in. Oh, sorry. Should be dy, because here your parameter is y. Negative 3 to 2y cubed plus 4 minus y squared dy. So y to the fourth divided by 4 plus 4y minus y cubed divided by 3 and 2 negative 3. And then when you plug in 2, you have oh, I made a mistake. Here you have negative 2y. So here you have negative. So when you plug in 2, you have negative 32 over 4 plus 8 minus 8 over 3 minus negative 2, 81 over 4 minus 12 plus 27 over 3. Okay, then what do you have? So we can simplify it. This cancel out with this. So negative 8 over 3. And then here you have, this is negative 40 and 1/2. And for this one, you have negative 3. This is 9, so negative 3. Therefore, you have 40 1/2 plus 3, so 40 1/2 plus 1/3, 40, 5 over 6. Okay, so I would like to make 2 remarks. Remark 1. So make sure your parameterization is from the initial point to the ending point. Well, when we discuss the line integral of the second kind. Recall we remarked before, for the first kind, you can choose whatever orientation you want. You can go from the initial to the ending or from the ending to the initial. Both work. But here, you need to make sure that, so because otherwise, if you flip the direction, we get an extra minus sign. So for example, let's suppose we still continue the above in the above setting. Let C to be negative C1. That is occur from 0 to 2 to negative 5, negative 3, and the given by a parabola for minus y, x equals 4 minus y squared. If you draw the picture, you have this, but then the direction is this. Okay, then if you do parameterization, parameterization. It's the same. You can take the same parameterization, but then the problem is x is 4 minus y squared, y equals y. But then the problem is your variable y is changing from changing from 2 to -3. Although the region is still like this. Okay, so usually we take this parameterization and do the following. I will show you another method which is more rigorous, but when we do computation, we usually don't use that one. So that means when we do calculation for this, we still use the parameterization. We still use the usual method. I will leave here. So we do y integral, and inside everything is same. 4 minus y squared times dy dt1 and dy. And then the key point is now, because you are from 2 to -3, you put the bound here. This is legal and this notation because you can define it to be -3 to y squared. And yeah, by all the calculus rules in calculus 1, you just flip it, and actually that's the definition when you have larger lower bound than the upper bound. Okay, then you will find the answer will give you extra minus sign here. And if you want a little bit rigorous one, but I don't recommend you to use this approach, use more rigorous parameterization. That is, you set y to be -t, and then x is 4 minus -t squared, and then t is from -2 to 3. Okay, then blah blah, you can do the remaining calculation you will find. So this parameterization just compatible with the orientation. But in this problem, probably you introduce the third variable, a little bit more tedious, but if you have a hard time understanding the orientation part, you can take this as a parameterization. So to end the remark, so I would choose a parameterization. Compatible with the direction of the curve for second kind. So you either choose this way or choose this way. Method 1, method 2. Okay, next, so the second remark, what is the second remark? Yeah, I will come back to that later. So first, we do another example. So here we do 1D. Okay, so the example. we generalize it to 3D. Similarly, in 3D, we can define the line integral of second kind to be PQR dot with dx dt. Sorry. Dot with gamma prime t dt. So t is from A to B. So we define it to be like this. And then some other notation might be used in your physics class. So suppose F is just P, Q, R, and then just as before, we might write down this as P dx Q dy plus R dz. They have the same meaning. No matter what, when you compute, you have to go to this. You have to go to this. So these two are just two different notations for the same thing. Okay. Next, let's look at one more example. I is y dx plus z dy plus x dz along C. So where C consists of the line segment from 2, 0, 0 to 3, 4, 5, followed by the vertical line segment C2 from 3, 4, 5 to 3, 4, 0. Solution. Oh, I remember the remark 2 I want to make here. We will discuss later. So remark 2 here. So IC1 is different from IC2 in our case. Okay, so solution. So first, let's draw the picture. This is from, first one is from 2, 0, 0, X, Y, Z, 2, 0, 0 to 3, 4, 5, 3. And then 2, 3, 4, 0 goes back to the XY plane. This is C1, this is C2, go this direction. Okay, to solve that, we just compute one by one. So first, for C1, we can choose the parametrization just as before. We use interpolation. 1 minus t times the initial point plus t times the ending point, and write down the formula in coordinates. 2 minus 2t plus 3t. Okay, and then the answer is t plus 2. And for y is 2 minus 2t plus 4t is 2t plus 2. Sorry. For y, since you have 0 here, so since you have 0 here, you have 0 plus 4t, which is 4t. And for z is 0 plus 5t is 5t. and then t is from 0 to 1 because we use interpolation. Okay, then for probably we can first compute the integral I1 defined to be integration from along C1 first, and inside you have y dx plus z dy plus x dz. We plug in the formula, so you have integration from 0 to 1. Y is uh, 4t, and dx dt. So I will omit this. So dx dt here is 2. Here's 1. So dx dt is 1. Dy dt is 4. dz dt is 5. Times 1 plus z is 5t times dy dt is 4 plus x is t plus 2 times dz dt is 5, and then dt. And if we simplify it, we have so 20 what do we have? We have 29t plus 10. It's 29 over 2t squared plus 10t, 10. So 49 over 2. Okay, now let's look at C2. And the parametrization for C2, you use the same method. Is 1 minus t times 3, 4, 5 plus t 3, 4, 0. And therefore x is 3, y is 4, z is 5 minus 5t. T is from 0 to 1. And then what do you have? We have I2 defined to be integration along C2, y dx plus z dy plus x dz equals 0 to 1. Y is 4 times dx dt is 0 plus, so dx dt is 0, dy dt is 0, dz dt is negative 5. Okay, and the plus z is 5 minus 5t, dy dt is 0. X times dz dt negative 5 dt. So it's negative 15 dt. It's negative 15 t, 1, 2, 0, negative 15. So the total integration will be I1 plus I2 because you have two adjacent small curves whose union is your original curve C. So we have 49 over 2 minus 15, so minus 99.5. So it's positive 9.5. Okay, next let's look at one more example. Suppose you have integration of the second kind. So the vector field is given by xy I plus yzj plus zxk, and c is given by x is t, y is t squared, z is t cubed, 0 between 1. Here the parameterization is already given, so it's pretty straightforward. We write in the vector form and then we take derivative. You have 1, 2t, 3t squared, and then we use the form. The I is integration f dot f prime t dt, and then it's from 0 to 1, 1 t squared t. So here is position for f. F is xy. Xy is t times t squared. Yz is t squared times t cubed. Zx t cubed times t dot 1, 2t, 3t squared dt. So it's t cubed plus 2t to 6 plus 3t to 6. Okay, and integration from 0 to 1. So t4 over 4 plus 2t7 over 7 plus 3t to 7 over 7, 1 to 0. So it's 1/4 plus 5, 7. Okay, so 27 over 28. This one is pretty easy, straightforward. Just want you to get familiar with the vector form. Okay, now let's turn back to the to this example, the first example we discussed. You had two curves with the same starting point and end point. And for the line integral, for the green one is a little bit easier to parameterize and calculate. A little bit easier. And for the yellow one is a little bit more difficult, more involved. Okay, so when you do math, you should be greedy and think crazy. So since they have the same ending point, you might ask, so can we compute green one but get the answer for yellow one? This seems crazy, right? Because they are different curves. Okay, but then people find, so the quick answer is no in general. See our example. But this not end the story. You might ask another question. When it is possible? When is it possible? Okay, so next we had the following theorem. So if f is a gradient field, then integration of green one equals to the integration of yellow one. If the starting point, so gamma 1 A equals the starting point of the yellow one, and the starting point of the end point of the yellow one equals the end point of the green one. So for example, so here C1, C2 are arbitrary. As long as they have the same, for example, you might have this, and then you have this, and this parameterized by gamma 2, and so this is gamma 2A, gamma 2B equals, gamma 2B, gamma 1B, gamma 1A equals as soon as these two curves has this property, then it's true. Since the proof is easy, we will show it here. Oh, by the way, so this is a claim that you can compute the yellow one by green one, and then if moreover you know the potential for the one of the potential for the function for the vector gradient vector field F, capital F, then you even don't need the green one to compute it. You can directly write down the answer. You just evaluate the potential function at the two endpoints and then do the subtraction. Minus F gamma 1 A. Okay, and the proof is easy. So since F is gradient field, vector field, so there must be some small f such that capital F is divergence of the potential function f. Then we have this dr equals gradient f dr, and then we recall the parameterization is like the following, and then we have integration from a to b gradient f, just fx, fy, fz, and dot gamma 1 gamma so gamma prime. So gamma prime is dx dt, dy dt, dz dt, and then we do the dot product. So you have this partial dy dt plus partial f partial z dz dt and dt. Okay, then for the quantity in the parentheses, you can recognize this by applying the chain rule. This is just df dt times dt. Okay, now by the, or if you still cannot recognize it, you write in this way. Then by the fundamental theorem of calculus, in 1D, you have this is FB, or Newton-Leibniz rule. you have FB minus FA. Oh, sorry. Here, to be more rigorous, we should write in this way, gamma 1 T. F gamma 1 B minus F gamma 1 A. Okay. Now let's look at one easy example for the gravitational field. So suppose the vector field is given by this, and don't be afraid of the constant. It's not that useful in this course. And the C is a smooth curve. So it could be arbitrary. You don't know what it is, from 3, 4, 12 to 2, 2, 0. And compute fx times dr. Okay. So the integration fx times dr. And here we have a solution. We know the potential before. This is given by the following function. X1 square, x squared x squared plus y squared plus z squared, or in some variable you prefer. If you prefer x1 squared plus x2 squared plus x3 squared, or in some notation, just length of the position vector. Okay, and then the integration. The only thing you need to care about is end point minus initial point. So this is f. Okay, so you need to figure out the here. Okay, so the tricky part is here. So the tricky part, we don't need to have the value of the parameter when we use the formula here. When we use let's call star. When we use star above. And the only data we need is the coordinates. It's a coordinate of 2 points, of the 2 points. So initial point and end point. So therefore you don't need to know what is the parameters. The only thing, you can just plug in this and this into your function here or here. So therefore I is F3, 4, it's 220. 220 minus F3, 4, 12. And if you do a little bit of computation, you have M, capital MG, 1 over square root 8 minus 1 over 13. Okay, I will stop here.